Start.
Okay, so welcome to everybody. Welcome to this AJS. Today with us we have Harshith Gowrachari. He is a PhD student here at SISSA MATLAB. And today we'll talk about nonlinear transformation techniques for model reduction of advection-dominated problems. So Harshith, the stage is yours.
Thank you, Anna. So good afternoon, everyone. Thanks for coming. And today I'll discuss our nonlinear transformation techniques and like few recent developments which I have worked on and also developed recently for model order reduction. So this is my overview. I'll give like a brief motivation and the brief theory of model order reduction and more details on nonlinear transformation techniques and its application and some conclusion of these techniques and those limitations. So I think my few of like mine is an industrial PhD. I work with one of the like industrial collaborators called Danieli, who produces these machines which are used for steel productions. So this is mainly the one of the best way of producing molten like steel slabs, and it's one of the best practices with which you can produce green steel and without wasting without having much wastage. So in this, I particularly model the Tundis, which is an intermediate tank between the mold and ladle, and which is basically a multi-phase phenomena, and like it has heat transfer and buoyancy effects and also turbulent. So this Tundish goes through like 4 phases and 3 steady and 3 transient phases and 1 steady operation. And this is it goes to 3 transient operation when they are changing the ladle during the startup and also at the end of sequence when the tank is emptying. So this is like the figure I'm showing. This is a molten steel. As startup, it starts increasing, and once the ladle changeover happens, it starts decreasing, like the level goes down. And this is basically a multi-phase phenomena, and which are governed by hyperbolic PDEs. And we are mainly interested in developing a reduced order model for this. So this is just basically a model reduction in a nutshell. Like, let us consider equation Q for this PDE and solution manifold of n dimensions, which consists all the solutions in the given time interval. Model reduction is basically seeking for a low rank approximation of manifold M in space nu n, which is of dimension n, which is much lesser than n, which we can obtain by mainly having a fast decay of singular values of your snapshot matrix, which basically contains all the solutions for the given k time intervals or parameters. The key idea of reducer modeling is mainly to construct this low rank n-dimensional space and to evaluate these reduced solutions in this reduced space. And one of the reduction, like model reduction barrier, is mainly can be known by knowing the Kolmogorov n width of your solution manifold, which is basically like this is the Kolmogorov n width of a solution manifold MZ, and which shows us the error we accumulate by approximating the function M of MZ with any element of G in En, which is basically a linear subspace of dimension En, and which also tells us like faster the Kolmogorov n with decay as N increases, it's better. It's more likely that we have a good way of finding a good linear approximation space of small dimension to approximate your solution manifold. And we can find this linear approximation subspaces by performing linear dimensional reduction. And one of the main strong assumption of linear dimensional reduction is like you can decompose your solution manifold into few linear combinations of few global phases function, and which can be decomposed as such, which is a summation of your global basis, which are also called modes and coefficient matrix. And you basically obtain this modes by performing single value decomposition, which is a linear dimension reduction basically. And single value decomposition mainly used for linear dimension reduction, as I mentioned, which can be decomposed into these three matrices, where U is like use which contains left singular vectors, which has POD modes, which kind of represent the structure of your data, and the sigma, which is a diagonal matrix, which has a diagonal entry of singular values, which are arranged in an increasing order, and which indicates the energy contribution of the corresponding modes. So one of the main challenges for model reduction is like you can see for heat equations, like which are different diffusion problems. For that, you can have like quite sharp decay of singular values. Or even for linear advection equation, you don't have a sharp decay, which is quite important for developing an efficient reduced order model. And so there are few techniques to overcome this. So there are few techniques to overcome this limitation of slow Kolmogorov decay or a single value decay of your solution manifold. First is you can work on developing a reducer model on nonlinear trial spaces, which you mainly obtain by nonlinear reduction using convolutional autoencoders. And like another approach is the quadratic approximation manifold. And another one is updating your linear subspaces, and which like usually when you perform reduction, like your basic is fixed. In this case, your bases are also parameterized, so you have a different basis for different predictions which you seek for. So this is also one of the approaches. And another approach is transforming your linear subspaces, where most of the techniques which I have mentioned here, like you basically transport to one of the reference configuration, and then you perform reduction, and then you push back to the like so-called physical configuration again. So here today I explain, like I kind of extend this topic shifted POD, and like the extension of that work. So today I'm going to discuss about these two nonlinear transformation techniques. One is neural network shifted POD, and another one is Radon Cumulative Transforms. And this is like the first one. I'll discuss neural network shifted POD, which is like extension of the shifted POD. And I'm going to complete, like my work is basically to complete this paper. This is only offline. Like I'm gonna extend it, like also include online phase, like to have both offline online workflow. So yeah, as I mentioned, neural network shifted POD is the extension of shifted POD. Like the main idea of shifted POD is like you choose a reference configuration, and you are basically transporting all the snapshot to this reference configuration by constructing a shift operator that acts on this function, which transports all the snapshot to the reference frame. And in shifted POD, you are doing this by shifting the space by a quantity BT, and B is basically a advection velocity at which your field moves. And for this methodology, like you need to know this advection velocity a priori. This is one of the main limitation of this. And to overcome this, like what the we or in the previous work they proposed is to use a neural network to learn the shift operator. And here the shift operator is a function of both space and time, and which automatically detects the shift for each parameter. and it's not a linear depending on time as it was for shifted POD. So this workflow has basically two neural networks, naming InterpNet, which we use to mainly to reconstruct the reference configuration. For shifted POD, you have to choose one reference configuration, which your InterpNet will try to learn and reconstruct at each shifted spaces. And we use ShiftNet to quantify the optimal shift for a given parameter. And once you have your training, like once you learn the okay, let me explain. Okay, first you train the InterpNet, which tries to reconstruct the reference configuration, and for each shifted space you reconstruct again using the InterpNet and try to minimize the Euclidean difference between the Euclidean distance between the reference on the and the reconstructed snapshot in the shifted space. And these are the two optimization problems which we're gonna minimize in this workflow. And this is the implementation as how it goes. So first, you train InterpNet, which kind of reconstructs your reference snapshot. And this is the ShiftNet part. For each shift, you reconstruct a snapshot at each shifted space. And until you have you get to the desired tolerance as you want. And then after your ShiftNet as desired tolerance, it returns the optimal shift for a given parameter. And with this, you have you do the shift of your snapshot, and with which all the snapshots are in the reference configuration. And then again, you have to interpolate this fields in the physical space. For that, we use a linear interpolator. And using that, we reconstruct all the snapshot in the at the reference position in the physical space. And this is very important to obtain the sharp Kolmogorov inverse decay. So this is okay. I think I missed few. Okay, I skipped one slide. Okay, this is we consider a toy problem for 1D Gaussian waves where we parameterize the mean value. As the mean value increases, you can see the distribution moves, which basically mimicking a 1D wave. So here I'm choosing one of the snapshots as a reference configuration, which InterpNet tries to reconstruct. And this is how the ShiftNet operates. For each shifted space, it reconstructs the shifted locations. And you're trying to minimize the distance between the reference and the shifted. That's what it's showing in the plot. And this is before and after pre-processing. And after this transformation of your solution manifold, and you perform reduction, basically by performing single value decomposition, and you find R number of modes, which basically you obtain by seeking for R number of non-singular values, which gives the most energetic modes. And using that, you obtain a modal coefficient simply by projecting your modes onto the data. And to predict for new unseen parameters, you have to build a solution manifold approximation, which you're basically mapping the parameter to the constructing a mapping between the parameter and the model coefficient, which you can do by using several regression techniques, linear interpolation or Gaussian process, or radial basis function, or neural networks. And yeah, this is how you can reconstruct for a new unseen parameter. And so, and this is the rest part of the algorithm. So you have the transform manifold, which I showed earlier, which everything in the reference configuration, and you perform reduction on this transform manifold, and you obtain the most energetic POD modes, and you do solution manifold approximation. And this is everything is in online phase. And in the online phase, all your predictions are still at the reference configuration, because you do reduction and manifold approximation also only at the reference configuration. So again, you have to shift back uh, like this, and again you have to do interpolation to get back to the physical space. And now your predictions are in physical space. This is how you do the predictions for the in the online phase. And this is I'm comparing singular value before and after pre-processing. And first POD mode is sufficient for the reconstruction, since it has the most energetic. And this is the predictions for the test parameters for this case. Okay. And we have considered two hyperbolic PDs for numerical experiments. One is considering isentropic convective vortex, which is governed by 2D unsteady Euler equations, as shown. And we try to impose the vortex in the domain by considering this analytical solutions, and which is and with given vortex strength, and also the radius is also equal to 0.5, and at the vortex center is this much. This is the initial conditions for this. And we consider a domain of 40 cross 20 discretized into 28,000, almost 29,000 grids, Cartesian grids, and the time interval between 0 and 62.5, and with a time step of 0.0, and which yields us 100 snapshots. And for this, since like this test case is mainly is very popular for higher order methods, so the, so we use for numerical methods, for to obtain this solution, we use this library called finite difference hyperbolic PD solver on Cartesian gates, where they have implemented this fifth order Vino scheme and third order stability preserving Runge-Kutta schemes, which is recommended in all the numerical experiments people are doing in the community. So I'm following the same steps. So these are the snapshot. I'm showing few snapshots at time 0.6 and 25, and this is how the vortex evolve over time. I'm just showing for 3 time instances. And this is after doing the shifted POD approach, where you can see the vortex is always in the reference configuration, which is now, and I'm comparing with the original snapshot. And I'm also comparing the singular value decay. And here for reconstruction, I'm only using one POD mode. And this is the predictions for the test set parameters. And yeah, I'm just showing 3 in time instances. And these are my reconstruction error, which mean relative error is 1.8 to the power minus 5. So I think it's good enough. And another test case we consider is two-phase flow, again, which are governed by hyperbolic PDEs. Here we consider unsteady Navier-Stokes equation. And for interface capturing approach, we consider volume of fluids, which is a quite popular interface capturing approach in the community, and in which they solve the volume fraction advection equation simultaneously with continuity and momentum equation, and which is basically this, and where alpha takes a value between 0 and 1. For gas, it's equal to 1, and for liquid is equal to 1. And at the interface, it varies between 0 and 1. And this is basically a one fluid model, and which the velocity is shared between both the phases. And the physical quantities of fluids are average over time, and which is given by this equation. And the turbulence model we consider is K epsilon turbulence model. And so we consider a domain of 2 cross 1 discretized into this number of cells, and time interval of 40 seconds and time step of 0.05, and which yields us 800 snapshots. And for numerical method, we can say finite volumes. And to have a and to have a good boundness of your scalar field, which is alpha, which should vary between only 0 and 1, we consider this popular Mule's scheme, which is mainly used for multi-phase flows. We're considering this, which is a semi-implicit second order numerical scheme. And then for time integration, we use the Euler implicit first order. And here I'm just showing three time instances of two-phase flow, how it's evolving over the time. And this is basically a filling tank problem. Like as your time increases, you see the fluid level increasing. And for this case, even after, like here, I'm choosing the last snapshot as my reference. You can notice that even after shifting, we don't have we don't gain much. We don't notice a sharp decay of singular value. For this specific reason, what we were trying to do was like to introduce like new penalty terms in the shift operator, so that we always fill this gap with the fluid, like to have this portion as blue. And then we tried few things, and the best way was to just use the interpolation and to reconstruct the reference configuration for each for each parameter. That's what we did. Like we mainly use the interpolator to transform all the snapshots to reference configuration, with which we have a sharp decay, and we are using this uh, first POD mode for reconstruction. And these are the predictions for my test set parameters, and can see it predicts the locations pretty well. And you can, there's slight differences in the field values at the interface level, which is quite expected for this. And these are my reconstruction error, like for training and test set, and which is of 6%. So the next part is radon cumulative transforms, which is widely used in image classification, in computer vision, and image processing. So the first part is radon transform, which is basically an integral transform. And like this is a formal definition of radon transform of so given a function f in the two-dimensional plane, the radon transform of function f is basically an integral of the function along the line in all the directions and the angle available, and with which you basically represent your function in terms of its line integrals, and which are mainly used used in which are used widely in image classification. And one of the main usage in this process is it's used in transforming your high dimensional signal to a series of 1D signals. And the next is cumulative distribution transform. So this is a very formal definition. So if we have two signals, let's consider one as input signal f of x and the reference signal r of x. Both are positive and normalized such that it's equal to 1, which is basically a probability distribution function. And the forward CDT of function with respect to reference configuration is defined as a strictly increasing function f of x, that's which should satisfy this relation. I mean, with this, I mean, you cannot understand much. So the main idea of CDT is it's basically an invertible nonlinear signal transform, which maps your given signal defined in a probability distribution function to another space such that it's minimizing the Gaussian distance between the the input signal and the reference signal. And for the CDT considers both pixel intensity variation and the location at which you have this pixel intensity variations. And radon CDT is a combination of both, where you break your high dimensional signal into a series of 1D signals, and then you use CD2 to transform these variations, which are basically Lagrangian, which includes both displacement and intensity variations, to Eulerian, which mainly includes intensity variation without having this Lagrangian or displacement movements in the LTD space. And it is the main advantage of CDT is this, with which we can notice a sharp Kolmogorov decay in the transform space. So this is like a overall workflow of developing a resort model using Radon Cumulative Distribution Transform. So you have your input, basically snapshot, which you have to normalize, and then you perform radon, and then you do CDT, and then the radon and CDT, and then you do reduction, and with which you have a sharp decay, as you can notice here. And this is the without this is just in the physical plane without doing any transformation. This is after the transformations, and then you build your reduced order model at the transform space in a RCDT space, and then and you also do predictions in the RCDT space, and then you do inverse CDT and then inverse radon to get back to physical space.
You are solving the same linear advection equation here of the Euler vortex.
This is not my work.
No, but still, what they are solving.
I think this is like a Gaussian way.
There is any diffusion or only?
Yeah, this is actually like it's convecting all over the.
But there is no diffusion, right?
No, there's no diffusion. It's advection. Yeah. So these are a few conclusions, like Tollier transformation accelerate Kolmogorov decay to find the small linear subspaces for approximating a solution manifold. And there is a full workflow of developing reduced order model, which includes both offline and online phases. And it's it's applicable for specific problem. It cannot be generalized approach. And one of the limitation of nonlinear shifted POD is the advection field shape should be constant for all over the time interval. If the feature or the shape modifies, I don't think it's the best approach. And even like actually in paper, LCDT claim that there is no loss when they are doing the transformations, but it introduces intrinsic transformation error, and which we should be including, and further studies should be investigated. And then for few applications which they have reported in the paper, like some in near the boundaries, it takes 0 values after the transformations. So for that, you need to do pre and post processing, which is basically a trial and error method, like so, which will improve the applicability. And these are the few recent developments and those application in different spatial domains. I think the most promising, I think this is what they claim, but I think the most promising is adaptive basis and adaptive sampling approach. And then, yeah, so thank you.
Thank you, Harshith, for the interesting talk. So, are there any questions here from people in presence?
So thanks for the talk. The first is regarding the first part. about the shifting dynamic. So if I understood correctly, the second part, so you have this ShiftNet and the InterpNet, no?
Yeah.
The idea of the InterpNet is just to have the possibility to reconstruct the solution at any given point in the mesh. Like you are shifting your point and then you want to evaluate there.
Yeah.
But so that's quite, I would say, if the domain you want to approximate is quite complex, then this map is actually quite costly and difficult to learn. Like, for example, like in your second example, it was probably something like 20,000 nodes, something like that, right? Yeah, exactly. So here you need to understand this. You need to find this map from, let's say, two-dimensional positional point to which is the value of the solution in that point when shifting. But can you just why one can choose just the finite element method interpolated on the solution? Like because also the coupling in the algorithm is so the InterpNet is just separated by with respect to the InterpNet, right? So in this exactly.
Okay.
So here you learn the InterpNet and
Yeah.
then you use the InterpNet just as a model, right?
Yeah, we just use it like
Exactly.
for reconstruction.
Yeah. So but this is also adding another layer of a reconstruction error, right? So like if this model is
I know, but
some error, then you are
like for this the tolerance is 10 power minus 6.
okay,
I mean
but for this
for this.
exactly.
Yeah.
No, once that you have a finite element solution, which is your reference solution, then you can just use that model as a model, like just interpolating the.
No, but for this, I have tried to use that, but since it's in tensors, so you cannot just like convert your interpolation into tensor. It doesn't. The workflow is not smooth. That's why they are using to like InterpNet as an interpolator,
Okay.
and which you are using for reconstruction in shifted space. Like the workflow is not smooth if you're using interpolation for reconstruction at the ShiftNet level.
Okay, because you need you have to use the interp, but you're not doing the backpropagation on the InterpNet, right?
Once it's trained, no, we are not using it again. Like once it's trained.
Okay.
Yeah, you basically learn first reconstruction and then you learn the shift by reconstructing a different spatial location to find the optimal shift.
Okay.
Yeah.
Unlike this, there is no backpropagation.
Okay.
Yeah. You just train once. No, you train once. Yeah, that's all.
Yeah, since it's the couple I was thinking about, let's say, if one removes the constraint that you have to learn this map to interpolate, so like, since the first is just a model to interpolate, then you can also change however you want that kind of model.
No.
Different ways of interpolating, because like if you're just using that, let's say that you want to learn a map for a super complex approximation that is not a square or whatever, then that task will be quite complex and is also adding another layer of
No, I have tried this.
Okay.
The thing is I have used the normal linear interpolator for reconstruction. And when you're calling this in the ShiftNet, when you're reconstructing, you convert to tensors and then the workflow is not. That's why I think that's one of the reasons why they are using this.
And instead, let's say for the second part, how complex it is to construct this Radon transformation? Like, so you have this model of deduction pipeline, and you say, as with the ShiftNet, I guess you want to convert, do some kind of pre-processing of your snapshot and then apply it. So with this Radon transformation, no?
I mean, the pre-processing is just like, you mean the snapshots?
Yeah, exactly.
I mean, you just have to normalize that.
Okay.
Like no, like this is you have libraries for this. Okay. You have a couple of libraries.
What is going on there? Like it's like a Fourier transform or
this Radon transform, which is an integral transform. We are basically dividing your like a function into line integrals.
Okay.
Yeah.
Okay.
And then CDT, you are minimizing. For CDT, it's basically like you're minimizing the persistent distance between your reference and your input signal.
Yeah, it's just a different,
yeah,
a different
approach.
way of transforming everything into a
Yeah,
reference solution
yeah,
and then use that reference
yeah,
solution to
yeah,
do that.
yeah.
Okay.
Yeah, the main idea is the same.
Yeah, no,
But this is more, I mean, if this works, the RCDT, I think this is like even for it's time you're not wasting too much time training your network. Like this
I
is,
see, I see.
it's
Yeah,
like
so
this is
what-
just transform, like
Yeah, yeah.
poof, done.
And then you expect, let's say, which of the two approaches you expect to work better also with when having, let's say, some kind of diffusion in the model? Because like here you have only clusters, right? So you have one model. But what happened, like, so at least in most of the cases. So if you also have a diffusive way, like which of the two you expect to be, in a sense, easier?
I think Giovanni has a paper for, if I remember correct, this made
Yeah, definitely.
Yeah, for sure, the neural network shifted theory won't work.
it won't
The
work for
interface
yeah.
changes its shape.
Yeah, because then
No,
you have
no,
only-
if it's
Yeah, exactly.
if it's diffusion, shifted period doesn't
Even
work.
if it changes its shape, like normal shock become oblique shock, so it will.
I mean, I think this is like RCDT should have more chances of yeah.
It's kind of generalizing what
Yeah.
we're having, but
Yeah.
let's say also for a bit more, like because here you have been nonlinear transformation.
Like this is the best property of CDT, which transforms your displacements and also intensity variation into Eulerian framework. Just intensity variation by adjusting the intensities, and then also you can do inverse. So
But since it is used for image classification and those kind of application, I believe this has some potential when your interface is changing.
Yeah,
I feel like, I don't know.
Yeah, no, I would think the same. Yeah, that's why I asked. Yeah, I saw.
I mean, yeah, it could be a try.
Yeah, possibly, because the other one, the method shows it does not have much hope. But here, possibly yes, because it has some applications in the image classification to represent it in different space.
Yeah.
But it can be solved easily. Yeah, possibly.
I think-
We can investigate further on this.
I think in paper there is this numerical experiment of this jet flow. Maybe you can have a look.
Okay. I mean, even idea is that how complex the flow is, that's not the issue. Issue is that how complex the flow is changing. Like circle is becoming square, something like that. So if that is getting solved, then it's a good thing.
Yeah, also, I mean, you can have a look at this. Like they have this numerical experiment.
Yeah.
You can see online. They have the video. You can see like the wave solitons. It kind of deforms and then it's propagating, and they have a really good prediction.
Yeah, but
Like, I'm
still-
not showing
still
here.
It is not changing its shape.
No, it's deforming. It's like,
Okay.
but it's not like completely. But
Okay,
yeah.
makes sense, makes sense.
it's changing the size and then also propagating in 3D domain.
Okay. Also shape is getting changed.
Yeah.
Okay, then I would say you can focus more on this because it has more promise for computational mechanics.
Sure. Thank you.
Any other questions here?
More you
Yeah, I just wanted like maybe if you can go, maybe I lost it, like, how do you think to generalize the shift plot for online prediction?
generalize shift port. Okay. This. You mean this?
Yeah, in the online prediction.
So you do your reduction and manifold approximation at the reference configuration where all the snapshots are transformed.
Yeah.
And then, and for given parameter, you have a predicted snapshot at the reference location, and you shift back. Like before, you do x minus shift. Here you are just adding the shift. And then you have to do the linear interpolation with the shifted space and the predicted snapshot values, and you reconstruct in the physical space by passing at the physical location, which is x. And this is just an interplay between shifted space and then getting back to physical space.
But how will you perform the interpolation in the physical space?
This is linear interpolator. I'm using linear interpolator. Yeah. Yeah, like I mean, I had better pictures, but I didn't want to put too many. To-
Any other questions here? I have a curiosity. You said that you trained in the same training process, the ShiftNet and InterpNet, right?
Mhm.
So you have a unique training, basically.
So, I mean, first you train your InterpNet. Like this is you train your InterpNet.
Okay, no.
And then you
There's
finish the
two
training. Yeah, there are two training phases. One is for InterpNet, another is for ShiftNet, where you're calling the InterpNet for reconstruction at each shifted space.
And how long did it take,
Uh,
the whole process?
no, like for this two-phase case with this
Yeah, this,
2000 grid points,
okay,
half an hour.
half an hour.
Yeah.
Okay.
For this case, it was yeah, this is like almost 29K. I think I spent like half a day.
Okay.
I don't know whether I should find the right parameters. I mean, I found the right ones for the two-phase flow.
Okay. It's more complicated, of course, with this case dimension.
I mean, for this case to work, I kind of have to pre-process the data to make it work for this. Yeah, it's not the whole story.
Okay, any questions from the online part?
What did you mean with
Yes,
pre-process
just
the
unmute
data
yourself.
there? Actually, you said you had to pre-process the
No
data.
questions, so
Just a question of reality. So like the single values you're plotting there are the one of the snapshot you're bringing back to the reference, right?
You know, the black ones, yeah, everything is in reference. Yeah.
Okay, so ideally, I mean, if it's like completely just is there no diffusion and your map is like exact, you should have just one more.
Yeah. I mean, also, I mean, I'm not, yeah.
And then it's also an unfair comparison in a way, because you're bringing everything back to one single dimension, and then you're comparing actually evolution, which is supposed to be independent in a way.
Yeah, that's why it's applicable for a particular problem where your feature is not kind of evolving or diffusing. That's what I mentioned, like applicable for specific. Like two-phase, like for my specific case, like the one with this, like here interface is like evolving very slowly. Like you don't have much like diffusion or like breaking of interface. For this case, I mean, it works. Okay. We still have to implement for this case. But that was a toy problem. Yeah.
Thank you.
Okay, so thank you, Harshith, for the nice talk again. And I think we can stop here. We will see the next AJS. So thank you all.